Chapter 15 is on power series and Taylor series. Before we go to power series and Taylor series, we need to start with sequences and a convergence test in section 15.1. This is very similar to what you had in calculus before going to power series. And everything is very, very similar to what we had in real calculus, except that, here we're dealing with complex numbers rather than real numbers. So this is how the sequences are defined. An infinite sequence, or briefly a sequence, is obtained by assigning to each positive integer n a number zn, called a term of the sequence. So we call them z1, z2, z3, and so forth. We write them in curly brackets like that, z1, z2, z3 as like a set, or we can write that in curly bracket as zn. That shows the general form of the sequence. And a real sequence is the one whose terms are real. So this is more general. It could be real, could be complex. And convergence, by convergence, we mean when the sequence has a limit c. What it means is that when n goes to infinity, zn goes to c, or simply zn approaches c. The formal definition of limit is that for every epsilon positive, we can find an n such that the absolute value or the distance of zn minus c, zn and c, is less than epsilon for all n greater than this n. So when I say the limit is c, you say how close these can get. I say as close as you want. And so you give me a number, say it's 1 billionth. I want these Zn to get within 1 billionth unit of the C. So you give me an epsilon, which is 1 billion. Then I look around and find an N and find a number, for example, a billion or a few billions. And then it says for all N greater than that number, all of these terms of the sequence are closer to C than epsilon. I mean, they are in the epsilon neighborhood of C, which is like this. This is C, this is epsilon neighborhood. You say after some point, all of these are inside, no matter how small the epsilon is. You make it smaller, I find a larger n so that this satisfies, and so forth. So this means the limit is C. If I can do that for every epsilon, I can find an n. Means the limit is C. All right. In real sequences, we didn't have a disk here. We had only an interval around C, between C minus epsilon to C plus epsilon. And we said that for n, all n greater than some value, all of these xn fall in this neighborhood. All right. So very similar, but the only difference is this here. So convergence and divergence. We want to see if different sequences are convergent or divergent. You can check, for example, is I to the n convergent or divergent? I'm going to ask you, what do you think? Give me your answers by this. You should look at how it behaves. I to the n becomes I squared, I cubed, I fourth, and I to the fifth, and so forth. How it behaves, and is it divergent or convergent? All right. I guess that's all we get. So most of you said convergent. Anyone wants to comment on that?
So for this one, typically when we see over n, it means, and it goes to infinity, your answer would be 0. So I would guess convergent. Where I could be wrong though is, I know you're supposed to compare like rate of growth and which one increases faster. And I don't remember which one does, so I just assumed the bottom would increase faster, so you'd get 0.
That's right. You see the I to the n. Yeah, very good. I to the n has a magnitude of 1, right? It jumps around. But then when you divide by n, it becomes smaller and smaller, get closer and closer to 0. So let me see here. For for n equal to 1, we have 1, and then becomes negative 1/2, then becomes negative 1/3 of I. And then, so that's here, and then becomes closer and closer and closer. See, it spirals into the center. And if the thing is, if you increase n, it becomes closer and closer to 0. So whatever, however close you want it to be to 0, you can consider a small circle over there, a small neighborhood of 0. After some time, all of them will be, after some time, all of the terms will be within that neighborhood. They don't come back, and they get closer and closer to 0. So the convergence is correct. All right?
Professor?
Yes.
So the second part of that explanation, do you know, like off the top of your head, the list of functions and which one increases in growth faster?
Yeah,
like
it doesn't matter if it, the numerator here, I to the n, has a length of 1 always.
Yeah.
And
Oh,
then,
no, but I'm talking more in like
yeah.
feature convergence and divergence, because it's like when you compare.
Oh, we're
like
going to
n
talk
factor.
about that.
Oh,
Yeah,
okay.
we're going to talk about that, yes. Okay, thanks for asking. We're going to get to it very soon. What about this one? Can somebody shout out? If you look at the, somebody says divergent, which is correct. For n equal to 1, you are here, right? 1 and 1. This is I plus 1. If you square that, it becomes 2. Then square that, it becomes here. And then square that, it goes here. And then square that, it goes here, right? So, and then get farther and farther. You remember we said that this is 1 plus I is square root of 2 e to the I pi over 4, right? So if you keep raising the power, the module of these numbers become 2 to the power of n over 2. So goes up, right? Or a square root of 2 to the power n. So goes bigger and bigger as you increase n. So it never approaches anything, okay? This is 1 plus I. This is 2I, and it's 1 plus I cubed, and so forth. It goes 45-degree angle increasingly, and then it also increases its module. So it goes as it spirals out. So it is divergent. Okay. All right. So what are series? Given a sequence Zn, we may, for this, form a sequence of sums. We call Z1 S1. We find S2 by Z1 plus Z2. S3 is Z1 plus Z2 plus Z3. So Sn in general is the sum of the first n terms of the sequence. So Sn is Z1 to Zn. And Sn is called the nth partial sum of the infinite series, or simply we call it the series Sn. And we write it like that: sum of m from 1 to infinity Zm is Z1 plus Z2 plus Z3 and so forth. A convergent series is the one whose sequence of partial sums converges, means that this Sn converges for that. So limit of Sn becomes S. Then we write S equal to sum of these Zm's. And call S the sum or value of the series. So if the limit doesn't exist, and it is not convergent, we call it divergent. All right, so if the sum of all of these terms it has a limit, then we call the series convergent. If it doesn't have a limit, we call it divergent. This is about the remainder. Remainder of this series after Zn is called Rn. And if Sn has a limit, Sn goes to S, then Rn goes to 0, obviously, because S is Sn plus Rn, and Rn is S minus Sn. So if Sn approaches S, Rn approaches 0. Now we have tests for convergence. This is what you asked. How do we know if a series is convergent or divergent? We have tests for it. The first thing we want to know is that if the series converges, then limit of Zm is equal to 0. So if you see a series that limit is not 0, limit of Zm, the limit of the sequence is not 0, then the series diverges. For example, remember I to the power n. When n approaches infinity, this doesn't go to 0. All right. So that means this doesn't happen. Therefore, the series is not convergent. If the series is convergent, this has to go to 0. So if this doesn't hold, means that the series diverges. You see, we say P, then Q. Means that P then Q doesn't mean Q then P, but it means not Q then P, then not P. Means if the limit is not 0, then the series diverges, is not convergent. All right. So a good example of this is when the Zm goes to 0, but the series diverges, is a harmonic series. Remember, harmonic series was 1 plus 1/2 plus 1/3. In general, series of 1 over n diverges, even though 1 over n goes to 0 as n goes to infinity. So this limit going to 0 doesn't necessarily mean convergence. This is a good example. The harmonic series. If the terms go to 0, but the series diverge. Absolute convergence means when the series of the absolute values converge. So if you have a series Zn, and we have the series of the absolute values converge, we say that this series is absolutely convergent. All right. If Z1, Z2, Z3 converges, but absolute values don't converge, then the series Z1, Z2, Z3 is called conditionally convergent, not absolutely convergent. One of the examples of conditionally convergent series is this series of 1 over n alternatingly negative and positive. This is like sum of -1 to the power n plus 1 divided by n. This becomes, this is convergent. But it is not absolutely convergent because the absolute value of these become all positive, becomes the harmonic series, and that is divergent. All right. So sometimes we have conditionally convergent series. If the series is convergent, if the series is absolutely convergent, it is convergent. And we have comparison tests that you can use to decide whether a series is convergent or not. For example, if you have a series, you want to see whether it is convergent or not. And you can find another series, it's called B1, B2, B3, and so forth. And that series is a non-negative, has non-negative values, terms, and it is convergent. And you have each one of these is bigger than the corresponding term in the other one. Then you can decide that if the bigger one is convergent, the smaller one is also convergent. So if absolute value of Z1 is less than B1, absolute value of Z2 is less than B2, and so forth, then the given series Zn is absolutely convergent. That means that in short term, if you have a bigger series and it's convergent, the smaller series is also convergent. All right. We have geometric series, which is this series that you had in real numbers, 1 plus q squared plus q cubed, and so forth. Adding all of these, if q is less than 1, then this is convergent, and the sum of the series is 1 over 1 minus q. If q is larger than 1, this is divergent. In the complex numbers is the same. If absolute value of q is less than 1, this is convergent and converges to this number. If absolute value of q is 1 or greater than 1, this diverges. Of course, this negative is if greater than 1, definitely diverges. But for some values equal to 1, it may converge still. It comes like that alternating positive negative of harmonic series can be convergent. And we have a ratio test that says if you have a series of Zn with positive terms, has property that for every n greater than some n, absolute value of Zn plus 1 over Zn less than or equal to q that is less than 1. You see here, it doesn't say this is less than 1. It says less than some number that is smaller than 1. That's very subtle. Means, for example, you see the series 1 over n. Zn plus 1 is 1 over n plus 1, and Zn is 1 over n. And if you calculate the limit of this becomes n over n plus 1. This is smaller than 1 for all values of n, but gets closer and closer to 1, and it is divergent. So it means that there should be a gap between the limit of this and 1. All right. So this should be less than a number that is less than 1, and Q is less than 1 and it's fixed. And if that happens, then the series converges absolutely. If for every n greater than n, absolute value of Zn plus 1 over Zn is greater than 1 or equal to 1, then the series diverges. All right, so this is ratio test. Another way to put forth this ratio test is this. If a series Zn with positive values, positive terms, is such that limit of Zn plus 1 over Zn is equal to L as n goes to infinity, then if L is less than 1, the series converges absolutely. If L is greater than 1, the series diverges. But if L is equal to 1, we cannot conclude anything. The series may converge or diverge, so that the test fails and permits no conclusion. So when this is 1, you cannot say anything. But if it is more than 1, diverges, less than 1, converges. Okay? So this is the same ratio test, but explained a little bit better this way. So, for example, for harmonic series, this becomes 1. You cannot conclude that. You have to use other methods to show that it is divergent or convergent. And for -1 to the power n plus 1 over n, again becomes 1, but this is convergent. So you cannot tell by if this limit becomes 1, you cannot tell whether it's convergent or divergent. What do you think about this one? Sum of 100 plus 75i to the power n divided by n factorial, which is this series, is it convergent or divergent? Let me give you the poles. What do you think? All right. Anybody else? I have 70% of the answers in. I give you a couple of more seconds. All right. All right, I guess that's everyone. All right. Mostly you said convergent and some of you said divergent. Does anybody want to share their thoughts?
I chose convergent because n factorial, I think, increases a lot faster than the numerator.
All right, so that's a good thought. All right, anybody else? Yeah, same thing. All right, yeah, that's good. You can do that. Yeah, n factorial is as after some n, it becomes greater than any z to the power of n. But that is just hand waving argument. You can do the same thing here. Just you can just calculate Zn plus 1 over Zn, see what you get. So if you calculate Zn plus 1 over Zn, that means 100 plus 75i to the power n plus 1 over n factorial divided by 100 plus 75i to the power n divided by n factorial. And you see, you get a lot of cancellations. The result will be 100 plus 75i absolute value divided by n plus 1. And the absolute value of 100 plus 75i becomes 125 divided by n plus 1. And that goes to 0 as n goes to infinity. All right. So that's the reason we say that n factorial is stronger than any power. So it becomes 0 because it's less than 1. The series converges absolutely. In particular, it's convergent. All right. Any questions?
Can you explain how you go from the absolute value of 100 plus 75i to 125 again?
Oh, this absolute value 100. Yes, sure. You see, this is a complex number that has just 25, 50, 75, 100, and here is 25, 50, 75. Right? This is this, and the absolute value of that is the length of this line, which is 175, right? Because this is 4 times 25. This is 3 times 25. This becomes 5 times 25.
Thank you.
3, 4, 5 right triangle, right? All right. Any more questions? All right. Yeah, it's okay. Root test. Root test is this. It's if you have a series Sn and we have limit of absolute value of Zn, nth root of absolute value of Zn as n goes to infinity equal to L. Again, if L is less than 1, it is absolutely convergent. If L is greater than 1, it diverges. If L is equal to 1, again, no conclusion. That's called root test. All right. Now, power series, 15.2. What are power series? Power series are the same as real calculus. You can write them as sum of an and z minus z naught to power n. In real calculus, we had an x minus x naught to the power n. And you can expand it and write it like this, right? So z is a complex variable. A naught, A1, and A2, and so forth are complex or real constants called the coefficients of the series. And Z naught is a complex or real constant called the center of the series, means, or we can say expanded around Z naught. This generalizes the real power series of calculus. So it's exactly the same, but generalized to complex numbers. If Z naught is 0, we obtain as a particular case a power series in powers of Z, and it is called Maclaurin, sorry, around Z, around 0, sorry. Power series have variable terms. You see, these are there are Z here, so it means that for every Z they are different, right? It is a function of Z. But if we fix Z, then all the concepts for series with constant terms in the last section apply. Usually a series with variable terms will converge for some Z and diverge for others. For a power series in situations is simple. The series converges in a disk with the center Z naught, or in the whole Z plane, or only at Z naught. All right, there are only 3 cases. Either it is only convergent at Z naught, or it is convergent in a disk around Z naught, or in the whole plane. All right, and we're going to call this radius of convergence later on. And radius convergence is either 0 for just one point, if it is only convergent at the center, and it is finite, or it is infinite. It's very simple. Geometric series here is convergent for absolute value of z less than 1, means that inside the unit disk, and it diverges if absolute value of z is greater than or equal to 1. All right. And of course, if I think this is written a little bit carelessly, because if absolute value of z is equal to 1 and z is equal to -1, then becomes a series that is convergent. It's it doesn't consider that. It should say diverges if the absolute value of z greater than 1, not equal. In equal case, we cannot tell. This is the material from the book. There are some cases where the power series converges for all z values, the same as this one. As you saw in that case, you just saw was z was 100 plus 75i. Here is in general z to the n divided by n factorial. This is again because n factorial is stronger than any z value. This is convergent for any value of z. To prove that, we can just do the ratio test. Z to the n plus 1 over n plus 1 factorial divided by z to the n over n factorial. It becomes absolute value of z divided by n plus 1. And as n goes to infinity, this goes to 0. So you see that it is always, no matter what value z has, it goes to 0 as n goes to infinity. So therefore, it is convergent for every value of z in the complex plane. And some examples are only convergent if z is equal to 0. For example, here, n factorial z to the n. This series is only convergent if z is equal to 0. And to prove that, you can do this. Zn plus 1 or an plus 1 divided by an, absolute value, is n plus 1 factorial z to the power n plus 1 divided by n factorial z to the power n. And you see that z to the n cancels, so you get z in the numerator, and n plus 1 factorial over n factorial becomes n plus 1. And this goes to infinity as n goes to infinity for any value of z. Z is fixed, remember. Z is fixed, but n goes to infinity. For every fixed value of z, this goes to infinity. Okay? So means that for any z, fixed z, for any value of z in the complex plane, this is divergent, and it is only convergent at z equal to 0. All right? So we have this arguments about convergence of power series. Every power series converges at the center. This is for sure, because if z equal to z naught, all of these terms become 0, and this values of the series becomes just a naught. All right? If one converges at a point z equal to z1, which is not z naught, it converges absolutely for every z closer to z naught than z1. Okay, means this: if the series is convergent for this z1, then for every point that is closer to z naught than this z1, means every point that is inside the circle of this radius centered at z naught, the series is convergent. So it means that if you find a number at which the series is convergent, for any closer number to Z0, it is also convergent. So that narrows it down. It becomes very easy. And if it is divergent for this Z2, it is divergence for any point that is farther away than Z2. So also that's very useful. So that enables us to define radius of convergence. What is the radius of convergence? We consider the largest circle with center Z0 that includes all the points at which a power series converges. Let R denote its radius. The circle absolute value of Z minus Z0 equal to R. See, this is a circle with center at Z0 and radius R. Is called the circle of convergence, and its radius R is called the radius of convergence. The theorem implies convergence everywhere within that circle. That is for all Z for which absolute value of Z minus Z0 is less than R. You see, this is a disk or neighborhood. All right. Of neighborhood of Z0 with radius R. Right? And the series diverges for all Z for which absolute value of Z minus Z0 is greater than R. So because this is the largest circle that has all the divergent points in it, so you have everything here is convergent, everything outside is divergent. At any point outside, the series is divergent. So say this R, and this is Z0. R is the radius of convergence. All right. That's the figure. All right. No general statements can be made about the convergence of a power series on the circle of convergence itself. The series may converge at some or all or none of the points. So here are examples. The circle of convergence radius R equal to 1 in all three series. The radius is 1 for all of these series that we are going to show. And you see for Z squared, Z to the n divided by n squared, converges everywhere on the unit circle, because 1 over n squared is convergent, so this becomes convergent at any point under the unit circle. For this one, Z to the n over n diverges at 1, converges at -1. When Z is equal to 1, becomes harmonic series, so it diverges. When Z equal to -1, becomes that series that I told you, alternatingly positive, negative, that converges. And Z to the n diverges everywhere on the unit circle. So no matter if Z is 1 or -1 or any other value, it never approaches anything. But for any Z smaller than 1, of course, inside the unit circle, it converges. So the circle of convergence is still the unit circle, but this is divergent everywhere on the unit circle. This one diverges at some point, converges at some others. This one converges at all points on the unit circle. So that's why we cannot make any general statements about the circle of convergence in general. Okay. Or the radius of convergence is infinite if the series converges for all Z values, and radius of convergence is 0 if the series converges only at the center. For example, that Z to the n over n factorial, if this series is converging for all Z, so the R is infinite, we call it. And the other one n factorial z to the n. For that, r is 0. Okay. For any other series, there is a radius that is not 0, not infinite. I mean, there are some a lot of a series that have radius of convergence infinite and 0, but there's all different cases. So this is about a comment about the real series. Here in complex plane, we have radius of convergence around z0. So it is actually a disk. For real numbers, it is just an interval around x0. That is called radius of convergence. All right. How do we find radius of convergence? From this theorem. Suppose that the sequence an plus 1 over an, and from 1 to infinity, converges with limit L star. If L star is 0, then R is equal to infinity. That is, the power series converges for all z. If L star is not 0, then R is equal to 1 over L star. Of course, if L star is infinite, then R becomes 0. All right? And so therefore, R can be written in terms of this limit of an over an plus 1. So if you find this limit, that would be the radius of convergence. And if that limit is 0, means that the radius of convergence is infinite, means that the series is convergent everywhere. If absolute value of an over an goes to infinity, then radius of convergence is 0. What do you think the radius of convergence of this series is? Would you like to take polls here? You want this? This is a little bit, may need some calculation to answer. It's hard to guess. Ah,
I answered 2 just because of the like if you look at the term right next to the summation, how it has the 2n over the n factorial. I realize that's probably wrong, but that was my reasoning.
yeah. Oh, sure. You should calculate just as absolute value limit of an to an plus 1. See what happens.
Mhm.
All right. Let's do that. These are the coefficients in front of z minus z0, right? Z minus z0 to power n. So an is 2n factorial over n factorial squared, and an plus 1 becomes 2n plus 2 because multiplied by 2 times n plus 1 factorial divided by n plus 1 factorial squared. If you simplify here, you see you can write this. This is the numerator over this, right? And then this becomes the numerator also, and divide by this. All right, so you can separate them like that, and then this 2n plus 2 factorial becomes 2n plus 2 times 2n plus 1 times 2n factorial. So 2n factorial cancels here. And then 2n plus n plus 1 factorial here is squared becomes n plus 1 times n factorial, the quantity squared. And then n plus 1 n factorial cancels in here. You get 2n, you get n plus 1 squared in the numerator and this expression in the denominator. So it becomes n plus 1 squared divided by 2n plus 2, 2n plus 1. And what happens when n goes to infinity? You see only the highest power. Here we have 4n squared. Here we have n squared. So the answer will be 1/4, which was this one.
Professor, could you explain with a little more space how you got from the second equality to the third? Because I couldn't really follow the.
Yeah, all right. From here to here?
No, I understand that, the other
Okay.
step.
The next one is the definition of factorial. You see, we have 2n plus 2 factorial. So it means 2n plus 2 multiplied by all the integers below that. So it becomes 2n plus 2 times 2n plus 1 multiplied by 2n and so forth. This becomes 2n factorial, and this is 2n factorial. They cancel each other. So you get 2n plus 2 and 2n plus 1. Right? And for the other one also, see n plus 1 factorial is n plus 1 times n factorial. And this everything gets to the second power. Do you get that part?
Yeah, I just needed a reminder of how to
Mhm.
expand
Okay.
factorials.
Do you get it now?
Yeah, I think I just gotta get used to and practice those,
Yeah.
like the n plus 2 factorial stuff.
Yeah. So it's a just definition of factorial. All right, so becomes 1/4. So it becomes n plus 1 squared divided by 2n plus 2 times 2n plus 1, which is 1/4. All right. Any more questions?
Could you please put your writing back up?
My writing?
Yeah, thank you.
So it's unfortunate there's no, but I should have made more room to write more nicely.
Okay, I'm done. Thank you.
You're welcome. All right. So this is radius of convergence. So this, you see the Z naught is 3i. So if you look at the complex plane, 1i, 2i, 3i, the center is here, and the radius of convergence is 1/4. It's very small circle around 3i. Only this series is only convergent in that circle and divergent everywhere else. All right. All right, functions given by power series. If any power series has a non-zero radius of convergence R, its sum is a function of Z, say f of Z. Then we write f of Z equal to the sum of a n z to the power n. So, or we can expand this way. We say that this function is given by this power series, or is represented by power series. And if a function can be represented by power series with radius of convergence r that's greater than 0, then f of z is continuous at z equal to 0. So the continuity follows because you can write it as a series here, and each one of these are continuous. And especially that the series is convergent at that point. If a function fz can be represented by power series with any center z0, this representation is unique. This is very important because you cannot write a function in two different ways in terms of the power series around the same center. That's why, for example, all these functions have Taylor series. We are going to talk about soon. A Taylor series that are unique. It's always the same. For example, sine x, cosine x, e to the x, and all of that. You cannot write it any other way. And you can do operations on power series. You can do term-wise addition or subtraction. If you do that, addition or subtraction of two power series with radii of convergence R1 and R2 yields a power series with radius of convergence at least equal to the smaller of R1 and R2. And you can do term-wise multiplication. It's the same as when you do polynomial multiplication. Each term from this multiplies by all terms from that, and then you can collect the similar terms. Or if you do that, you get this kind of arrangement, which is called Cauchy product. Okay, we're not doing a lot of that, so I'm going to go forward. You can do term-wise differentiation and integration. So we call the derived series of the power series obtained from 1 by term-wise differentiation. That is this. See, if you do term-wise differentiation of this, each one of the z to the n become n times z to the n minus 1. So it becomes n a n z to the n minus 1, and n goes from 1 because the first one drops out, becomes 0. So get a1 plus 2a2z plus 3a3z squared and so forth. And term-wise differentiation of power series gives us a series that has the same radius of convergence as the original series. So this is very important. When you do differentiation, you don't change the radius of convergence, which is very interesting. And this is an example that utilizes this property. For example, this is the series of a combination of n and 2, means 2 objects out of n object combination, z to the n. You know, this combination formula n2 becomes n factorial divided by 2 factorial times n minus 2 factorial. So it becomes again n factorial. It can be, you can write as n times n minus 1 times n minus 2 factorial, and divide by 2 times n minus 2 factorial, and these cancel out. So that becomes 1/2 n times n minus 1. So you can write it this way, and when you cancel n minus 2 factorial, you get 1/2 n times n minus 1 z to the n. And here you can factor z squared with this 1/2, becomes 1/2 z squared, and then the rest of the summation becomes n times n minus 1 z to the n minus 2. Okay, and then if you recognize this is the second derivative of z to the n, right? you can do step by step. This is derivative of z to the n. This is derivative of n z to the n minus 1. So you can write dz of n z to the n minus 1, and that is derivative of z to the n, right? So you can write another derivative of z to the n, or second derivative of z to the n. As I said, if you look at this, you might recognize the second derivative of z to the n. So, so this series that we have in here can be written like this. And this can be considered as one series that has infinite radius of convergence, but this series has a radius of convergence that is 1. Therefore, this series, the whole thing has radius of convergence that is 1, because if you take derivative twice, it doesn't change the radius of convergence. And this squared multiplied by it again doesn't change its radius of convergence. So this original series is has the same radius of convergence as the geometric series, which has a radius of convergence of 1. Okay. And you can do term-wise integration of power series. Again, the power series a n over n plus 1 times z to the power n plus 1 obtained by integrating the series sum of a n z to the n term by term has the same radius of convergence as the original series. So again, these two have the same radius of convergence, which is important. We're going to see when we are manipulating the series, you'll see that this is very important. We can just use that. All right, so power series represent analytic functions. This is very important because you see all of these things that we are doing is for analytic functions, and power series represent analytic function. Therefore, if you work with analytic, if you work with power series, in fact, you're working with power series of analytic functions. So a power series with a non-zero radius of convergence R represents an analytic function at every point interior to its circle of convergence. The derivatives of this function are obtained by differentiating the original series term by term. All this series thus obtained have the same radius of convergence as the original series, and therefore, by the first statement, each of them represents an analytic function. So working with power series is very good because you can represent analytic functions with them, and then taking derivative and doing stuff with them is very easy. Then we go to Taylor series. Taylor series, as you remember, was a series like that. Any function can be written in terms of Taylor series around any point within a radius of convergence. And the coefficients come from this formula. And this is no mystery, because if you have f of z as a naught plus a1, oops, what happened? It has some functions that I don't understand. A1 times z minus z naught to the plus a2 z minus z naught squared, and so forth. And if you want to find a naught, you can put z equal to z naught. If you put if you calculate f of z naught, you see z minus z naught becomes 0, 0, 0. Every term becomes 0. You get a naught. If you want to find a1, Then you calculate f prime of z, and that becomes a1 plus 2a2 times z minus z naught, plus next one will be 3a3 times z minus z naught squared, and so forth. And then if you put z equal to z naught, you get a1. So f prime of z naught becomes a1. Now, if you do double derivative, then this becomes 0. You get 2z2, 2a2, sorry. And then plus 3 times 2, a3 times z minus z naught. Plus next one would be 4 times 3, a4 times z minus z naught squared, and so forth. If you now put z equal to z naught, means double derivative evaluated as z naught, you get 2a2. So a2 becomes 1/2 of double derivative evaluated at z naught. And if you do again triple derivative, let me call it 3, then this goes away, becomes 3 factorial a cube, a3 plus 4 times 3 times 2, a4 times z minus z naught, plus next terms, like the next one will be 5 times 4 times 3 times a to the fifth, a5, and z minus z naught squared, and so forth. So if you put the third derivative of z calculated as z naught, then all of these that have z minus z naught go to 0. So you get 3 factorial times a3. So a3 is 1/3 factorial, the third derivative evaluated at z naught. And the same way you can see that f to the 4, to find a4, you do 1/4 factorial, the fourth derivative evaluated at z naught, and so forth. So you have the coefficients come out like that. An is 1/n factorial, the nth derivative evaluated at z naught. All right, this is Taylor series. We had it in a real calculus, but we have the same in complex calculus. All right. And in complex numbers, we have also, we can write an in terms of these because the nth derivative evaluated at z naught could be written in terms of these kind of integrals. So that's not important right now, but it becomes important later. And all of these formalities that path has to be closed, simple closed path, and all that. This is Taylor series, and Maclaurin series is when z naught is equal to 0, means that expanded around 0. So that Taylor series is more general. All right. So a special Taylor series. They are exactly the same as their real Taylor series because the coefficients are the same. You see, we had the same formula for the coefficients in real calculus. Therefore, each one of the Taylor series that you had in real calculus, now we can have exactly the same in complex calculus. Nothing changes because the coefficients are the same. For example, 1 over 1 minus z becomes a geometric series, z to the n. So f of z is singular at z equal to 1. This point lies on the circle of convergence. So this is the neighborhood of convergence of this series. It's only convergent within unit circle. E to the z is z to the n over n factorial. I already talked about that when I was talking about exponential form of complex numbers. And remember, the book talks about it right here. By setting z equal to iy and separating the series into real and imaginary parts, we can have e to the iy equal to sum of iy to the n divided by n factorial. As I said, there are even powers and odd powers. Odd powers all bring an I, and even powers bring -1 to the power k, and also here. And you see that this is the series for sine of y. This is the series for cosine y. So becomes e to the iy becomes cosine of y plus I sine y. We talked about this before, but I had to assume that expansion, the Taylor expansion is the same, which is, in fact, it is. And then we have the trigonometric and hyperbolic function, cosine of z, -1 to the power n, z to the power 2n divided by 2n factorial. You see, just put every x that you had in the Taylor series in real calculus, now replace it by z. Everything works. All right. So the Taylor series of cosine and sine. And logarithmic function. ln of 1 plus z becomes z minus z squared over 2 and z cubed over 3 and so forth. And if you replace z by -z, you see the squares, the even powers don't change because -z squared is the same as z squared, right? But all of them become negative. So you can take a negative factor and becomes like that, ln of 1 over 1 minus z. You can move this to the power, becomes ln of 1 minus z to the power -1, so it becomes like that, and all of them becomes positive now. And then if you add these two together, or subtract, no, add. If you add these two together, then you get ln of 1 plus z over 1 minus z, which becomes twice only the odd powers, because the even powers cancel out. You see, this is z squared over 2, -z squared over 2 goes away. And powers of 4 also go away, powers of 6 go away. Only the odd powers remain. Right? All right, I guess I stop here. We continue from here next time. We need to get through this and go to next chapter, which is the main action. All right.